They changed my whiteboard in the other classroom, and it like really sucks. So I was really worried that I would come in here and it would suck also, but it doesn't. So great. They changed the screens though, and the technology and all that. So this is so new that we still got the peely stuff on there. We haven't peeled that off yet. Anyway, sorry. Just look, it's 6 p.m. I'm allowed to get a little distracted by weird things to observe. So couple of announcements. So all the quizzes and stuff should be graded with one exception. I was posting and about to release the grades for assignment 1, and then I had to go to class. So that's going to have to wait till I get home, but it's done. It's all ready to go. So I just have to, finish it up at home. So expect that tonight. If I missed anything, let me know, because I did have the 2 quizzes to grade over the break, because there was the one that was due on like the Monday, and then we had one due on Saturday, so I kind of had to do 2 of them. So that meant I had a pretty big stack. So if I missed your name or something out of like 170 papers, please email me. And actually, that's true in general. If you ever notice like a grade's not right, or I, because when I'm going through them, I don't look at names or anything like that really. So if you talk to me in class and didn't send me an email yet, like if you were just like, here, Travis, here's half of it's in paper and half of it's online. There's a decent chance I'll just forget that as I go through, and I'll just like write down, hey, you forgot this. And then you just email me, Travis, no, I didn't, dummy. You have it on paper. And I'll be like, oh, you're right, sorry. And then I'll fix it. So if you ever notice that I say something like that, like, hey, you missed half the assignment and you didn't, just let me know. I'll fix it. I am forgetful. But yeah, there's that. That should be all updated tonight. There is some exciting homework coming up. I know. Don't get too excited. Due October 26th. Okay, so the course outline says 26th. I do not like giving less than a week, so it's the 28th now. So I'm just doing some final touches on it because I'm still trying to I'm humming and hawing between like a few different choices for a graph theory question. So I just it's gonna be like midnight and I'm gonna be staring at like 3 questions. And I'm just like, I just gotta lock in. I'll just pick one. And they're all decent questions. I just haven't narrowed it down yet. So I'll post that tonight. And I'd like to give you a week to do it rather than 5 days. So that's why I've just extended the date. So it's due on the 28th now. We also have group project 1 due November 2nd, I believe. I'm going to put a question mark there because I don't remember the specific date, but I think that sounds right. So this is the one that you're allowed to work in a group on. It's a bit bigger and the questions are a little bit more challenging because you submit once, right, together as a group, so you don't have to worry about that as much. And there's going to be, so again, you guys have finished the Python class, so for them, they're halfway through it. So the programming stuff I'm putting on this is pretty light. Like we're talking some basic recursion, some stuff that can be done with simple loops, that sort of thing. So it's all stuff that you've done already. So the programming might be a little bit mundane for people who finished the full Python course, but it'll still be there and it'll still be math adjacent along with some programming. So it'll probably be like implement some recursive functions like the GCD or something like that. They're not complicated. So yeah, that I haven't posted yet because I'm trying to, again, choice paralysis. I have like 5 choices I could pick from, and I'm like, I don't know which one, and I should just pick one. But this will probably be posted, if not tonight, tomorrow. So you have lots of time to work on it. And work period next week for group project. So what that means is you can so next week, there's no lectures. It is just, it's like extended office hours, right? So you can come in, and this is my way of being like, this is all homework. This is the only homework in this class that I make you do outside of class is these assignments, the chapter review assignments. There's in class work period for it where you can ask me anything you want and work together and whatever. I mean, considering this class is at 6 p.m., I expect attendance will be great. But I'll be here no matter what. So, like I will come in here at 6 and I will leave at 7:20. So even if nobody shows up, I'll be sitting here. So that means if you're, let's say you're working on residence or something, and it's like 6:45, and you're like, ah, crap, I have a question for Travis. Well, I'm here. So, that's what that's for. So you can just kind of come in and work on it, and then it's not really homework, right? Because if there's 4 of you in a group and you're all working on it together, should be able to finish it in that time period. But most people end up wanting to work on these because there's programming questions and those are fun. So anyway, just wanted to mention that. I should say, like everything in my course, attendance optional. You know, it's what I say that specifically for the work period, but that's technically true for the entire course. You don't have to be here because I record it, right? So that's fine. Okay, I think that's all I have for announcements. So we're just gonna get into it. So we're gonna be. So the interesting thing about our topics is I have sort of like the 4 chapters, and they're all kind of like they're related but not super related, in the sense of like, okay, working in other bases is obviously a computing concept, but it's not really connected to graph theory or formal logic or anything like that, and it's not really connected to matrix algebra, which is chapter 4. But it is an interesting topic nonetheless. So the first thing I want to say about this, and it's the when I write this down, it's going to be like, wait, what? That is kind of weird. And that's that numbers, the idea of a number, is different from the symbols we use to represent it. So numbers are different from the symbols to represent them. So, okay, that sounds kind of weird, but it's actually not that weird when we really, really think about it. So, an example for the number 14. And throughout this section, I'm going to, because we're sort of hammering down and talking about the distinction between numbers and the symbols that represent them. When I mean numbers, I will actually write the word. So first of all, this word is one way to represent the number 14, right? Just the word 14. If I say 14, you know what that means, right? Just by thinking about it, there's 14 things. But in terms of symbols, there's the obvious one that we're used to, right? So this is base 10 Arabic. So this notation is quite old. It's not. That's why it's everywhere. That's why it's one of the most common representations of numbers. But here's an example of one that kind of disappeared, unless you like Rocky movies or Final Fantasy. Roman numerals, right? But this, despite looking different, these still represent the same number, right? So this is what I mean, right? These represent the same number, but the symbols used to represent them are different. Another one, which I guess if you're a prisoner, right, counting down the days on your prison cell or whatever, ticks or tallies. This is another one, which is sort of a more, or let's say a less abstract way of representing the numbers, right? You literally count the number of ticks, and that tells you the number you're representing. So these all kind of have, so there's a reason why this is the one that kind of survived. It's short, right? It's really short and succinct. This, obviously, if we wanted to write down 107, it's a lot of writing. This starts to get really cumbersome because Roman numerals have different sort of rules for, like, are we talking about 50? Are we talking about 100? Are we, it starts to get really weird with Roman numerals. So they, again, have the same problem of for really big numbers, they become hard to represent. But this base 10 Arabic numerals, it does not matter how big the number is, it kind of just scales infinitely, right? Now, when we're talking about symbols, these seem sort of mundane, but there's like, you could ask, okay, those are interesting. That's, we have questions about those, like why did we choose X as 10 as an example, right? And why is this is obviously, it makes sense why this is 1 and that's 2 and so on. Why is V5? Who knows, right? But nobody ever asked that about these symbols, right? We look at this, 1, 4. Does that have to mean 14? And I know you're thinking like, well, yeah, because that's what we mean by 14. But we just sort of decided that these symbols mean 14, right? Just there's no real rhyme or reason behind it, right? We just said, yeah, that represents the number 14. So we want to sort of explore that, right? Do these symbols have to mean 14? And of course, the answer is no. So these are the symbols that we use all the time for numbers, right? So I forgot where I was going with that. Sorry, I just kind of brain farted. But you can imagine situations where we would ask this question, right? I mean, if you already know about binary probably, right? And the way we represent that. We also have hexadecimal, which you are learning in web dev. So the concept of representing a number in a different way is not that weird from that perspective either. So let's just think, we want to, in math, generally speaking, when we look at something, like an objective study like this question here, do we have to represent base 10, 14 in this way? We want to abstract a concept, right? And when students ask, hey, what's the point of learning math, right? When am I going to do base conversions is what we're going to talk about. And it's like, okay, well, honestly, sometimes depending on the context, maybe you'll convert from binary to something, but probably not very much. So what are we trying to get here? In math, it's more about abstract concepts. So, problem solving skills. And in this case, abstracting something, because in programming, you can kind of see how that would be really useful, right? You're given, someone gives you a concrete example of a task or a situation, and they say, okay, now build a program that does a lot more stuff. Well, if you take that example and abstract the important pieces of it, now you can understand how it can function as a program and take extra inputs and vary based on those inputs, right? So that's what we're trying to do here. We're trying to abstract this concept. So let's really think about what we're doing. So think of the number 512. Imagine this represents money, right? So boom, now it's money. It's dollars in Canada. So you wouldn't represent $512 as 512 loonies, right? Like you just imagine 512 loonies, and that seems like a ridiculous amount of loonies, right? That doesn't seem like a reasonable way to do it. Although that's really what it means, right? It is $512, right? It is 512 loonies conceptually, but if you went to the bank and said, I want 512 loonies for my $512, they'd be like, no. So how do we represent it? Well, this is 5 $100 bills, 1 $10 bill, and 2 loonies or 1 toonie in Canada, because we do have a $2 coin. So this is the $100 bills, this is the $10 bills, and this is the $1 bill, right? So this sort of lets us abstract this concept, right? Because we've got this ones position, this tens position, and this 100s position. And when I start talking about positions like that, we're starting to get into like, this topic feels a bit like grade school in some ways, because we're talking about like counting and addition and stuff like that. But we're going to take this idea and try to generalize it. So let's talk about base 10 principles. So what really makes something represented in base 10? What are the core ideas of representing something in base 10? Well, there's sort of two pieces here that are important, and it's what the position is, what it really means. So if we look here, as we move to the left, each position gets worth 10 times more than the previous, right? So going from here we multiply by 10, and going from here we multiply by 10. So that's an important part that we want to capture. So each position is worth 10 times more than the previous. So this is called a place value. These positions are called place values. Okay. Because of that, each one of these positions is represented by a power of 10. So this right here, so we call this the ones, but that's 10 to the 0. This is 10 to the 1, and this is 10 to the power 2, right? So we start at 10 to the power 0 and multiply by 10. We increase the exponent by 1, multiply by 10 again, increase the exponent by 1 again. So they're represented by powers of 10, yeah? Okay, so that's one important part. The other important part is the digits that we use to represent these numbers. So all digits must be less than 10. That makes sense, right? You're not going to try to squeeze in 11 there, right? That's not a digit, that's 2 digits, right? That's 1, 1, right? So we don't do that. So all digits must be less than 10 and are a single symbol. So again, that means 1, 1 is not a digit, that's 2 digits. So if we need 10 objects in one position, exchange them for one more to the left. So think of it this way, right? I walk into the bank and I have 10 $10 bills. And I'm like, I would like a $100 bill. And they'd be like, okay, yeah, that makes sense, right? That's the exchange rate. You exchange 10 $10 bills for one $100 bill. So now when I'm talking here, when I say we want to eventually abstract this concept, what I really mean is there's nothing special about 10, right? We just chose 10. Well, why did we choose to work in base 10? I'd say it's pretty obvious. 10 fingers, right? So when we were developing the concept of counting however long ago, we literally probably counted with our fingers, right? Like children. So you can imagine a situation of like an alien species that has 12 fingers. And so then they worked in base 12. They counted base 12 pretty naturally, right? That's just the system they use. So the point is there's nothing special about 10. So we can cross that out, as I talk about, base 2 principles, right? So each position is worth 2 times more than the previous one, right? All digits must be less than 2. And a single symbol. If we need 2 objects in one position, exchange 2 of them for 1 to the left, right? So this is base 2, but we would also call this binary, right? That's another way to think about it. So if we have this exact same thing here, 5, 1, 2, well, we have a bit of a problem here. This is not a representation in base 2, right? Because we violate some of the conditions here. So, okay, this is the 1's position, multiplied by 2. This is the 2's position, multiplied by 2. This is the 4's position. But notice here, all digits must be less than 2. Well, this is already a problem. We have a digit of 5 and a digit of 2. So that doesn't work, right? So we want to make sure that this condition is satisfied. So we could do something like this. And that would be fine, right? Because all those digits are less than 2. So let's talk about the valid digits. Well, in base 10, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, of course. But what about base 2? We just have 0 and 1. Right? Because all digits must be less than 2. So 0 and 1. All digits must be less than 10, 0 to 9. But there is another extremely common way of representing numbers in computing, and that's base 16. This is called hexadecimal. You've already seen it in WebDev. Your color, if you want to do colors in CSS or HTML, they're represented as a 6-digit hexadecimal code. And you've probably looked at RGB values as well. RGB values go from 0 to 255, indicating how the intensity of from black to full amount of that color. It turns out that 2 hexadecimal digits is all the numbers from 0 to 255. So that's why that's the case. But the point is, we just write 16 instead, right? Nothing changes here. It doesn't matter. We still get base 16 principles. And it works exactly the same. But now there's a difference here. When we get to this point, we say, okay, well, let's write down all the digits, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, now what? Right? The point is, digits are a single symbol. So that means we can't write 1, 0, right? No, that's 2 symbols, right? 1 and 0, which we've already decided are distinct from each other. So at this point, we need to start inventing new symbols. We didn't actually invent new symbols. We just started using letters, right? A is 10 in hexadecimal. B, C, D, E, F. And so hopefully this gives like at least, we're going to talk about hexadecimal is going to be used in a lot of our examples to sort of drive home that that hexadecimal stuff that you see in CSS is not just some random thing that you just have to know. There is actually something going on here. But the point is, none of these are special, right? They all work just the same as each other. So one way to think about these different bases is we can think of them as languages. So we have the concept of numbers, and we communicate in different languages those numbers, right? So we have the language of base 2, the language of base 10, the language of base 16. They're just different languages. They represent the same concept, just differently. So who here knows a language other than English? Does anyone? Okay, cool. In that language, you know, what's this called? Oh, well, that's mundane. Does anyone have a language that is not just television, basically? I mean, it's not television, but you know what I mean. Actually, are there any objects here that aren't close enough to the English word? Table? Okay, there we go. Perfect, right? So that is very, very different sounding than table, right? That's why I said not table, because we were sounding kind of the same. They're not the same, but they're close enough. But so table has 2 different, very distinct sounding words in different languages. And that's kind of what we're doing here too, right? We're saying, okay, we've got different ways of communicating this. And because of that, we want to sort of be able to communicate with each other, right? So like we just did, right? Because I was like, that. Like, I mean, if we actually didn't speak the same language at all, I would just be like, and you'd probably figure out what I mean, right? You'd be like, you'd say, so what would you call this? Sure, yeah, exactly, right? And I would be like, okay, cool, now I know what that word means, and I can actually use it to communicate, right? So that's how we learn each other's languages. Well, no, that's not, because that would be it's a terrible way for me to learn a language if I just walk around the room and now I'm just like, right? That's not a good way to learn a language. Don't do that. But that's the idea, right? So let's develop a way to sort of communicate with these different languages, converting between bases. So that's what we want to do, right? We want to say, okay, someone has something written in base 16. I want to write it in base 2. How do I get there? So there's a couple of steps that we need to do. And fortunately, one of them, well, really both of them aren't terribly complicated, and they're sort of motivated by the money example still. But let's say as an example, let's convert the base 8 so we've got a base 8 number, and I'm actually going to use those symbols. 512 in base 8 to base 10. So I am translating from the language of base 8 to base 10. And this is something I want to draw attention to. This 8 right here is a subscript. No matter how many times I mention this, someone always misreads it. This is not the number 5128. Right? It is 512 subscript base 8. So don't misread that as being part of the number. It is a subscript. And it's something that it comes up somewhat often in programming where you'll see subscripts of things written down, but it's more of a math thing. So, you know, you see like capital X, lowercase I, that just says subscript I as some kind of index or notational thing. Same thing here. We're just indicating, hey, base 8. Not part of the number. Okay, so what we want to kind of do here is be motivated by this money example, right? So what we were saying is, hey, this is the $100 bills. How many do I have? 5 of them. This is the $1 bill or $10 bill. I have 1 of them, and I have 2 $1 bills, right? So let's kind of use the same exact idea here. I'm gonna write it exactly the same way, and then I'll kind of show you a way that I like to write it differently. So this is it's still the $1 bill. I'm gonna actually use the dollar bill example here. But now we're in base 8. So we use the base 8 principles here. So we just replace the word 16 to 10 with 8. Each position is worth 8 times more than the previous. So that means this is the 8th position. Right, we multiply by 8, and then we go again. So this is the $64 position, right? So these are weird denominations of currency, right? We've got a $1 bill, an $8 bill, and a $64 bill, right? That's really what's going on here. So now, if we want to convert to base 10, we're really just asking ourselves, how much money do I have, right? These are my denominations for my bills, but okay, at the end of the day, if I add up all of my money, how much money do I have? So that's what we do for converting to base 10. So converting to base 10 is answering how much money do I actually have? And again, we're used to bills being in denominations in base 10, but even in Canada, that's not the case, right? We have $5 bills, we have $2 bills. Well, not bills anymore, $2 coins. So it's not really that weird to have an $8 bill, right? Because I would argue having a $2 coin is weird, but we have one. So an $8 bill or coin is not that weird. So we just have to ask ourselves, how much money do we have? Well, I have 5 $64 bills, right? And I have 1 $8 bill, and I have 2 $1 bills, right? And I just add this up, and that tells me how much money I have. So it's $320 plus $8 plus $2 is $330. Oh my goodness. So if I had this weird denomination of currency and I said I had 5 $64 bills, 1 $8 bill, and 2 $1 bills, I'd have $330, right? Now, of course, when we're actually working in other bases, we don't use this currency example. This is just motivation, right? Explaining sort of the concept that's going on here. We're still dealing with the same idea here, just in a different denomination, different values for each of these. So, okay, let's do an example that sort of doesn't have all the money stuff in it, although I find that there are a lot of students who like thinking of it in terms of that money example. So if you're comfortable with that, then feel free to keep doing that. So let's convert the base blank blank to base blank. So my point here is that we have sort of, it doesn't matter what base and number we choose here, right? The process is going to be the same no matter what. So I can ask people for random stuff. Give me a base. Sure. Oh, sorry, we're going to base 10. We don't need that underlined. And give me a number in base 8. So remember, digits have to be less than 8. Some bigger than that, maybe.
7.
Technically true, but let's multiple digits. 75, perfect. We'll do that. Okay, so again, this is the same idea, right? It's just our numbers are different, and that's okay, right? It's well, actually, our base is the same, but that actually doesn't matter. So we're working in base 8. So like I said, I have a sort of, I have a different way of representing this, right? So this is fine if we're thinking in terms of like the money example, but I like collecting it in a table. This is called a place value chart. So in this case, we only have, I made it way too big. We only have 2 digits. I made it exactly as big. So we have our ones position. So this is always the, whatever our base is to the power 0, it's always going to be the ones position, always. And then we just multiply by 8 as we go along, right? So this is 8 times bigger. So that's 8's position. And so these are the digits that go in here. And again, same exact idea. This is saying we have 7 $8 bills plus 5 $1 bill, right? So this is 56 plus 5, 61. So if we were using, again, this denomination of currency, and I had 7 $8 bills and 5 $1 bills, I have $61, right? Using that money example. So, okay, we see that converting to base 10 is relatively straightforward, right? It's essentially just saying, okay, I've got a weird denomination of currency. Let's just add up all the bills, like all the numbers on the bills, and see how much money I have, right? So what about going the other way, though? So this is converting to base 10. So how do we convert from base 10? Okay, so let's again start with an example. And so we're going to kind of keep the same motivation here. So convert the base 10 number 324. Now, this is up to you. So I don't think many people do this. Technically, you could subscript it with base 10 if you wanted to indicate that it's 10. But we usually don't need that, right? Because if you don't have it there, it's assumed it's base 10, right? Because that's the one that we use all the time, right? That's the one that we mostly communicate in when we're talking about numbers. So if you don't write it, that's just the assumption that it's base 10, right? So we're going to convert that to base 5. Okie doke. So same idea almost. So we have to remember, what is the base 5 representation? Well, it's how many of those bills that I have in each position, right? So what goes into this box and what goes into this box. So it sounds like I'm going to need some kind of table like this. So let's go ahead and start by building one. I don't know how big it needs to be, so we're just going to kind of let it be decently big at first. So this is always the ones position, or our base to the power 0 is always going to be 1. And then we just make it 5 times bigger each time. So this is going to be the 5's position, right? We just multiply by 5. or 5 to the 1. Then we multiply by 5 again. So we get the 25's position, multiply by 5 again. And we get the 125 position. And one more time, 625 position. Okay, so if we look at this, we have to think, okay, so like I could keep going, right? I could just keep multiplying by 5, but suppose I have 324 loonies, and I walk into the bank and I'm like, hey, this is ridiculous. Give me, bills in a sensible way, right? And so they're going to look at this and they're going to be like, okay, well, you have $324. You don't get any $625 bills, right? Because that's more money that's a bigger denomination than the amount you have. So, okay, we're going to write a 0 then. But now the question is, if you had 324 loonies, how many $125 bills do I give you? So we just have to ask, how many times does 125 fit into 324? So 125, 250, then 375. That's more than I have, right? So 125 fits in twice. So that means if I said I have $324 and I asked for that in base 5 bills, you would give me two $125 bills. Right, this number right here. Okay, so now we've been given $250 in bills. Well, you still owe me money, right? You still have to give me some bills. So what do you have to give me? This is 74, I think. There's still $74 unaccounted for, right? You still have to give me more bills. So, okay, the next size of bill is $25 bills. So we ask, okay, I have $74 left that I need to be given bills for. How many $25 bills do I get? 2, yeah. So again, this example here is sort of easy to just, reason through without too much math. Now I have $24 that I still need bills for. What's the next size? $5 bills. How many $5 bills do I get? 4. So I take that and say I have 4 $5 bills. How many $1 bills do I get? 4 of them. And you've given me all of the bills that I need. So we've filled in this table, right? That's exactly what we want to do. If I have $324, I would get 2 $125 bills, 2 $25 bills, 4 $5 bills, and 4 $1 bills. So then that means the number 324 is in this base, 02244 in base 5, but we don't write the leading ones in front. So like this right here, this 1, the 0 is not useful information, right? So we don't have to write it. And so that's the representation of this number. So we can think of these sort of as, again, there's a currency analogy here for both of them, right? This is, I have these bills in this denomination. How much money do I have?
Wait,
Mhm.
why is it that here you do not give the exact money? I don't really understand what I mean. So it's supposed to be 75, right? Dollars, no?
No, this is 75 in base 8.
And the 61 is in base 10.
Base 10. So this is, I have 7 $8 bills and 5 $1 bills. How much money does that total up to, right? So that's the concept of when you're in a base, this represents a number, right? So our goal is to say, okay, these symbols don't mean 75, they mean some other number now. What number is it? This one. This is going the opposite. This is the number we have, and we're saying, okay, this is the number I have. How do I write that in the language of base 5, right? So this is saying, okay, 324 is 2244 in base 5. That's how I would represent it. So let's repeat the previous exercise of, I'm going to get some random numbers. So let's convert the base 10 number blank to base blank. Give me a number. You don't have to be shy. I can be big. I can do mental math.
427.
Sure. All right, cool. And give me a base. Okay, perfect. All right, so this is the base we want to convert to. So we do the same thing. We say, okay, I'm going to have to build one of these. And it's always the same. So I start at 1. I'm writing these powers just for if that helps, but you start at 1 and you just multiply by 6 as you go to the left, right? So times by 6. So this is the 6th position. Times by 6 again, this is the 36th position. Times by 6 again, this is the 216th position. Now I could go again, but without even going one step further, I can look at this and go, yeah, but 6 times 216 is way bigger than 427. So I don't need to go any further, right? Because it would be 0. And so now we ask ourselves, okay, I have 427. How many 216s fit into that number? So it's a bit harder to see when the numbers get really big. So we can actually, there's 2 ways we can sort of cheat this. One way is, I'm going to need someone with a calculator. 427 divided by 216. What's that in a calculator? It's going to be 1 point something. 1.9, good enough, right? So the point here is that this is how many times 216 fits into it. So number of times 216 fits with stuff left over. Now, in this case, we don't much care about the stuff that's left over, right? We just care that it fits in once. So we write down 1, right? We would get one $216 bill here. So now we say, okay, 427 minus that one $216 bill, and we get 211.
Yeah.
And now we rinse and repeat, right? So now we have 36. So we say, okay, 211 divided by 36. It's probably going to be 5 if I had to guess, 5 point something. 5.8. So same thing. We'd say, okay, that part before the decimal, that's how many we write down. And there's some stuff left over. We don't care about it. But now we say 211 minus 5 times 36. This is 180, 31. It's a good number. This is a good choice. So now we have 31 left over, right? So I have to say, okay, well, how many $6 bills do I get? At this point now, it's small enough that we don't need to follow this process. But I mean, you still could. But I would look at this and say, okay, 6, 12, 18, 24, 30. So it's also 5 times. So this is 6 with 1 left over. So we're going to take this 5 and we're going to write it down. How many copies of the $1 bill do we get? Just 1. And we bring that over. So this is sort of one way to do it algorithmically, right? Instead of just, inspecting it and going, okay, how many times do I do this? So I've seen students in the past, they'll just say, okay, I have 324, and then subtract 125, subtract it again. Oh, I'm negative now. So when it took away twice, so that's how many bills I get. This is a slight improvement because now you kind of do it the same way every time, right? And our goal here is sort of capture an algorithm, right? Something that a computer could do. So we don't have to do it anymore. That's kind of the goal, right? Understand an algorithm. So if we do this sort of division and then subtraction, that sort of works, right? Because you can kind of see that, 427 divided by 216 is that number. We get this, and we write that down. And then we do the subtraction, and this kind of gets carried along, and we sort of have this path here, right? We have a bunch of variables here, right? This is our starting number. This is the place value we're working with. This is what we're going to put in our table, and this is the next step. Right, so you can kind of see how we can sort of loop over this over and over and over again. Okay. Now we sort of have two of the pieces that we need here. We now know how to go from base whatever to base 10, and we know how to go from base 10 to some base, right? So if I were translating two languages I didn't know very well, like let's say I'm translating French to Japanese. I don't really know either of those languages. So if I were going to do that, I would translate from French to English and then from English to Japanese. Now, with actual languages, there's a lot of problems with that because maybe I'm translating an idiom from French that doesn't exist in English and now I've completely lost the meaning and I can't translate to Japanese. But when we're talking about numbers, that's not the case, right? There's no loss of what I would say meaning here, right? If we go from one base to another base, it always means the same thing, right? There's no loss there. So we don't have to worry about that. But that can motivate us, right? So converting from one base to another. And that can include base 10 also, but if we have base 10, then we already have a way of doing it. So what I was saying here is, let's say we had base 2, and we want to go to base 16. That's too many e's. So my point here is I'm going to sort of do a combination of both these things, right? I know an intermediary language, base 10. And so what I can do is I can go from base 2 to base 10, and then from base 10 to base 16. Right? I can sort of do it in two steps. This specific situation, base 2 to base 16, your computer would not do this step because everything works in binary and the computers are that's what they do. They represent everything in binary. And these are both powers of 2, so it's really easy to convert one to the other, so your computer can just do it very directly. But for the purposes of illustration, we're going to go through the process here. And this is something that a computer does very, 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 very often because data is represented as binary, right? But it's not presented to you as binary. I'm sure if you've ever had, well, Python probably doesn't run into this, but if you programmed in like C or something, and you get a memory exception, like a pointer that doesn't exist or something like that, it'll give you some error in a memory address in hexadecimal. Because that's generally how memory is addressed in computers, is by hexadecimal. Also, if you've opened a program in a hex editor, that's a useful way to sort of pour through it and make changes to it, because 2 hexadecimal digits represents a byte, 16 bits. So that's why you would see, you look at a hex editor, it'd be like A, E, and then a space, and then 0, 2, and then a space, and 3, F, right? Like it's byte-sized chunks in when it reads it. So that's why it's useful. So let's actually work with this example here, right? Let's convert something from base 2 to base 16. So convert 0, 0, 1, 1 from binary to hexadecimal. So we're just going to combine these two techniques essentially, right? So we're going to first convert from base 2 to base 10. And that involves building our place value chart, which is going to be kind of big because base 2 is kind of like that. but we still build it the same way. So we got our ones position. I'm going to be lazy about it and not write the powers of 2 because it's easy to multiply by 2. 1, 2, multiply by 2, 4, 8, 16, 32, 64, 1, 2, 3, 4, 5, 6, 7, 128. Right, so these are the denominations for all of these values here. And we have 1, 0, 1, 0, 0, 0, 1, 1. Okay, great. So this represents some binary thing. So let's convert it to base 10. So the way we do that is, again, for binary, it's really nice because this is either a 1 or a 0. So you could save yourself time and just, if there's a 1 below it, you just add them all up, but I'll still write it out. So it's 1 times 128 plus 1 times 32 plus 1 times 2 plus 1 times 1. And so that is 160 something, 163. Cool. That's half of our journey, right? We've just gone here and we've done it. So now we need to do the next step. We need to go from base 10, 163, to hexadecimal, base 16. So base 10 to base 16. Okay. Same exact thing. We're going to build our place value chart. So when you're doing base conversions, you just build a lot of these, really. Again, it starts in our ones position. And then we have our 16s position because we just multiply by 16. And then we have our 256 position. And hey, we already don't need that, right? Because 256 bigger than 163. So we know this is a 0. Cool. So now we just have to ask ourselves, how many times does 16 fit into 163? So in other words, we want to fill in this blank, right? So that this is as big as possible. So how many times does 16 fit into 163? 10, yeah. So we have 3 left over. And we go ahead and write 10, right? Does that seem right? So there's a problem here, right? That's 2 digits, right? In base 16, we need something bigger than 9. So remember, we don't write 10 because that's the numerical representation. Base 16 is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A. Yeah, A, B, C, D, E, F. So instead of 10, we need to represent it as a single symbol. So this is the most common mistake that students make when dealing with bases higher than 10, is they will just write down 10 or 11 or something like that. But we have to be careful. Digits are single symbols. So this is A. But now we can continue along. So this is how many times does 3 fit into, or 1 fit into 3? It fits in 3 times. So that means that binary thing, 1010, 0011, is A3 in base 16. Okay, great. So this just seems like, okay, we just did the process, right? We went from base 2 to base 10 and then base 10 to base 16. But this is actually a relevant example. So I need to look at my notes to remember what specifically the symbol is. There it is. So this is what's the answer? Does anyone here know what UTF-8 is for encoding? You know what Unicode is? Okay, so do you know what ASCII is? So that's just like the normal characters on your keyboard, right? Like A, B, C, D, uppercase, lowercase, numbers, basic symbols. But there are lots of symbols, right? Like an unfathomable number of symbols, right? Like, I mean, technically on your keyboard, that's a symbol that you can type into text, right? You could type a smiley face. You can type an example. That symbol. Does anyone recognize that symbol? Just by chance. Yeah. So this is the pound sterling symbol. It's the British pound. That's what this is. This is the UTF-8 encoding of this symbol into binary. So what your computer does, there's a bit more in the background here. It actually does a bit more for validation of the encoding to make sure that we didn't have any problems. So I think it uses actually 3 bytes to encode UTF-8 symbols. But if you open like a text editor or something like that with this symbol in it, it will display properly. What is your computer doing? It stores it as this, and then it goes to a lookup table and says, this is the hexadecimal representation of that symbol. So when I see this hexadecimal address, display this, right? So this is like an actual real world example of what a computer does. I mean, it's a bit more complicated than that because computers by their very nature don't work in hexadecimal. They work in binary exclusively and yada, yada, yada. But the human readable representation of this binary symbol is this, which presents this to your screen. And UTF-8 encoding is pretty universal. It encodes most symbols that human beings write down that we know of. So yeah, it's pretty useful. So anyway, I just wanted to present that as like one, it shows you how to convert from base 2 to base 16 in a mathematical sense, but also it is an example relevant to computing both because it's binary to hexadecimal, and this is an actual example of something your computer does, right? It's UTF-8 encoding, which if you are interested in, I think even just the Wikipedia page can explain UTF-8 encoding. There's, again, I think it actually uses 3 bytes instead of 2 bytes to encode. So this is like a little, I'm skipping some of the stuff that you would include in the encoding, but anyway. Okay, so one thing I want to remark on about this algorithm is we're sort of doing this, right? And we kind of did that in our head. But when we think back to it, we did I said you could do this, right? 163 divided by 16 is going to be 10 point, I don't know, 2. Who knows? Some decimal number, right? Don't check my work. And then I was like, okay, we move this 10 and we write it down, and then we figure out essentially the remainder of this division, right? 163 divided by 16 has a remainder of 3, right? Well, we have a better way of doing that in programming, right? This, if we were to implement it in a program, which, spoilers, that's one of the projects, we can instead use integer division in Python, which is going to say that's 10, right? That's what the symbol does. It does integer division, which means we throw away the decimal part. And then you could say, all right, 163 modulo 16 is 3. Right? So, okay, when we're building this table, so we had, this is 16 and this is 1. So you can kind of see how we could store this as an array. You could use a dictionary too. This is going to say, hey, after doing this computation, take this number, put it in there. Oops, hold on. Don't put it in there. Go to a dictionary and look up what 10 corresponds to, right? That's A. Now take that and put it in here. So we got A from that. And this is the remainder that we are then going to perform the algorithm on again. So now we carry on with 3, and then we integer divide and modulo with just the next step in the list, right? So we just did 16. Now we move to 1. And what are we going to get? Well, 3 integer divided by 1 is 3. 3 modulo 1 is 0. We know to stop when we get to 0. We take this, and we're going to go into our hash table, and it's going to say 3 is the symbol 3. And then we go and we write that down, and that's our converted number, right? So this is a way to convert from base 10 to base 16 in sort of a very algorithmic way, right? This is, you know, this for loop is almost writing itself, basically, right? If you just keep track of your bases, which actually all you need to do is keep track of your position. So you know this is a 2-digit number. So then you could say 16 the power 2 minus I, whatever you're using for your loop or whatever. And then that would be this number, right? So there's lots of stuff you could do here to implement this, is my point. I'm just talking about it because it's not on the next homework. This one is for later. I think it's on the final programming project. I say, hey, implement a base converter that converts from any base the user tells you to any other base. So like I could say, hey, convert from base 4 to 11, and your program should be able to do that. But it's from base 2 to 16. I do say like, hey, it's not just any arbitrary base. You can't just do base 42 and I'm not going to expect you to have a hash table that goes up to like 1 million or something like that, right? No, it's only going to be base 2 to 16. So, okay, I hate what they've done to the room because now I don't have a clock anywhere. Okay, good. Which means I have more math to excite you with. Always. Whenever I say that, it's funny because I have had students. So when I say that, they're like, "Yeah, Travis says that all the time. He hates math. He doesn't really like math." I'm being sarcastic. I love math. I could do this for hours. Which I know people are like, "How can you do that?" Well, I mean, I love it. So I know students aren't enthusiastic about it, but I am. So we just talked about how to essentially communicate numbers in these other languages. So kind of the point here is twofold. It's one, get you some familiarity with base 2 and base 16 because you see it all the time, and you know it means something. So the hexadecimal codes that if you look at like F F F F F F is white in hexadecimal. So what does this really represent? There's sort of 3 things here. This is if you convert this, it's 255 to base 10. So this is how much red do I have? How much green do I have? How much blue do I have from a value between 0 and 255? So this is just a shorter way of saying that, right? Because you could say 255, 255, 255, and in fact there are even functions in CSS that let you specify an RGB value instead of a hexadecimal code. But this is just a lot shorter hand, and it's easier to fine tune, and doesn't need a special implementation because HTML is 30 years old or 40 years old or whatever, and it can read these codes. So the point here is one, to show you that, hey, these symbols mean something, and they are human digestible. Like if you see it somewhere else, it's the same meaning. But also, again, the idea is to take algorithms and sort of abstract them, right? Yes, we have this sort of idea of base 10 counting, but there's nothing special about 10 because we care about 2 in computing and we care about 16, but other bases work too. Octal is another one. Base 8 comes up in computing too because this individual piece could be considered an octal digit. Another thing you can ask is, okay, now I have this object of study. I see that, numbers and the symbols we use to represent them are independent from each other, but there are other things we can do to numbers, right? We can add numbers, we can subtract numbers, we can multiply numbers, etc. Is that base independent? Does the base matter? And actually, it turns out no, it doesn't. So we can do addition in other bases. And just like when we talk about base conversion, we're going to start with a motivating example of, okay, if we're going to abstract a concept, we should really understand how it works in the one that we really understand. So the reason why this is important is, again, in programming, you're often presented with, let's say, not the full picture of a problem, right? Like your end user, your client is saying, I want you to solve this. Here's the example I have. That's not what they want you to solve. That's just a situation they've encountered that they would like your program to handle, but their problem is way bigger than that. So they don't know it yet. So if you can abstract the important pieces of that, though, you can get ahead of that and build your code under the assumption that this will tackle more things. And of course, you don't want to reinvent the wheel. You don't want to over abstract and over complicate things and over engineer your problem. But the idea is, hey, when I'm given a simple thing, what are the pieces here that I can sort of pick out without the context of the specifics of the problem and sort of turn it into something else? And that's what we're going to do here. So we're going to start with base 10 addition. And we're going to see, how does this work? And what are the important pieces here that let us sort of abstract it into something else? So we've got our good old-fashioned long addition. So I think it was 20. Let's just do this. I'm going to write down random numbers. 8 and 3. So 28 plus 43, right? These are just two numbers. So if we were to actually do this long addition, which starting to feel like we're in like third grade again, but 8 plus 3, that's 11. So we write a 1 and carry a 1. 2 plus 1 that we carried plus 4 is 7. So that's 71, right? So what's really going on here? Well, this carry means something, right? Something is going on with that. So we can represent sort of pictorially what we have here. We have 2 green dots for that first number and 4 green dots here for the second number, right? So that's represents our tens position. Here we have 8, and here we have 3. And how do we add? We just dump these together, right? There's nothing fancy. We just say, okay, well, there's 6 green dots, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 blue dots. But that's the thing. When we're talking in base 10, we have a sort of exchange here, right? As soon as we have 10 of these, right, we trade them for 1 more here. And that's what this carry is, right? We said, okay, 8 plus 3 is 11. So that's too many, right? We can't write 11. So we have to write down the ones digit and carry. We exchange 10 of them for 1 to the left, and that's why we put a 1 there, right? So that's what's happening in the base 10 algorithm, right? Where we're exchanging 10 when we get to it for 1 more to the left. In other bases, the only difference is that exchange rate. Everything else is the same. So, in other bases, the only difference is the exchange rate. Right? Because here in base 10, we exchange 10. So let's talk about, what do I have here? Base 5. So we've got a base 5 addition, which if we want to indicate what base we're working in, we just subscript it here. So we've got, I'm using colors again for my own benefit. So we still do the kind of the exact same thing here. We just say, okay, well, it's 4 plus 4. That's 8. Now, if we were doing base 10, we would just write down 8. But we're not dealing with base 10, right? 8 is too big. We have digits 0, 1, 2, 3, 4, 5. Okay, so we right now, we're looking at something like this. 1, 2, 3, 4, 5, 6, 7, 8. So what we need to do is exchange 5 for 1 more, right, to the left here. And so that means we're going to carry a 1. What do we have left over? 3 dots, right? So we're going to write down a 3. Another way to think about this is we don't necessarily need the dot picture, right? We can look at this and say, okay, this is 1 of my base that I need to carry to the left with 3 left over, right? So I take this piece here, that's my leftover, write this right here, right? This is our carry. Because we went above 5, so we have to carry something. And now we can rinse and repeat, right? So this is 1 plus 3 plus 3, which is 7. Same exact thing. We say, okay, this is bigger than 5, so we need to carry something. This we have to carry. And what do we have left over? 2. We're going to write down the 2, right? The leftovers after carry. Now here we have 1 plus 4, which is 5. So that's bigger than 5. Well, it is 5. We have nothing left over. So we write that nothing, right? Just like if we did 5 plus 5 in base 10, we would write down a 0 and carry a 1. That's what we've done, right? We hit 5, so we carry a 1 and write down a 0. Well, we don't write these here, but these are all zeros, right? So this is just a 1, and we're done. So that means 3, 4 plus 4, 3, 4 in base 5 is 1, 0, 2, 3. So you kind of see here that it didn't change, right? The only thing that changed was instead of exchanging at 10, we exchanged at 5, right? And so when you're working on these, honestly, if the picture helps, you can use the picture. But eventually you do enough of them, you won't need it too much. And you'll end up getting lots of practice tomorrow, or not tomorrow. Day is it? Wednesday. You'll get practice on Wednesday. So with that, I will bid you farewell for the evening. And see you on Wednesday, where we will continue. We're going to do subtraction and multiplication. You can do division. We're not doing it because it's a lot.